So far this week we have studied the states of matter, solid, liquid, and gas, and the phase changes between them. And today we're going to look at two different graphical representations of these phase changes. One called the heating curve, which looks at change in temperature over time by adding heat energy, and the other is called a phase diagram, which looks at the relationship between temperature and pressure, which will impact the state of matter. Before we look at these graphs, I just wanted to go back to the practice, the foldable, because I realized I did not print them one-sided on your packets, so you won't be able to cut these out. So what I would do is, if you have access to a printer, print pages 4 and 5, one single-sided, and then you can cut out the pieces as needed and follow the directions. And then I would just cut out page 5 individually, and again you'll cut on all of these dotted lines to give you your little flaps. Okay, so that's just to clarify for the practice foldable. Okay, now let's jump into our graphs. We're going to start by looking at the heating curve. So the heating curve tracks phase change over time by adding heat. And we've talked about that temperature is related to kinetic energy of the particles. So the faster that the molecules vibrate together, it's what we measure as higher temperature. And so as the kinetic energy is increasing, the temperature will increase. And that happens when a state of matter is in a single phase. You'll notice, though, that there's a couple of plateaus, like this segment and this segment, where the temperature no longer changes, even though heat is being added throughout the whole amount of time on the heating curve. And this is because in those segments, the phase is actually changing. And so that energy is being used not as kinetic energy, but as potential energy, pulling apart the bonds, separating the molecules and the particles a little bit farther, so that we can see a liquid changing into a gas, for example, or a solid changing into a liquid, and those particles are being pulled further apart during that time. So that would be change in potential energy, which is not related to temperature change, only kinetic energy is. So with that being said, let's write down a few notes we just talked about. The heating curve will track phase changes over time. Okay. We've got temperature increase as kinetic energy is added to a single phase. Temperature remains constant during a phase change. We said that's because it is potential energy rather than kinetic. PE is standing for potential energy. So that's what we just kind of recapped. Now let's go into the phase change diagram. We'll get there. Heating curve graph, and label our parts. So this first segment, if you think about the temperature on the y-axis, low temperature is going to be down here at the bottom. High temperature is at the top. So our low temperature, kind of this AB segment, is representing solid state. And as if you think about ice, for example, as heat is added to the ice, its kinetic energy will start to increase until it reaches this specific temperature called the melting point. And during this time, the temperature no longer changes because now it is being used, all of its energy is being used to change from solid to liquid. And once we get to point C, now it's completely in the liquid state and continues to increase its temperature until we get to this second plateau where it starts to change again. Boiling, or vaporization is the broader term. Until it turns into a gas. And as the temperature increases, it will just stay a gas, moving faster and faster with its particles. So the information that you can get from a heating curve is the melting point. If you drag that over to the temperature axis, you can find the melting point, and you can find the boiling point for whichever substance you are observing its heating curve. So that's the usefulness of a heating curve, and it can give you a little bit of information about the energy of the substances. We will be using heating curves more in the future, but this unit we're just kind of looking at the idea behind it. The second graph we have is called a phase diagram, and the phase diagram uses pressure and temperature to kind of figure out what state of matter it would be in. So if you think about, again, temperature, low temperatures, which will be kind of on this left side of the x-axis, we're going to be dealing with things that are more like solids. And then pressure, if you think about how tightly the particles are packed, when things have higher pressure, that's when they're going to be the most tightly packed. So high to the left is representing our solid area. So that would be our A zone here. So A is representing solid for the substance. And then you can see our intermediate, our C zone, this is liquid. And then kind of the opposite, our high temperature, low pressure area, the B zone is gas. Okay? So anytime you have a phase diagram, it will follow this same pattern. Solid is our far to the left, liquid is the intermediate, and gas is far to the right. If we're looking at temperature, and then pressure falls as we discussed earlier. So there's two other points that I want you to be aware of. This point here where all three of the states kind of meet, this is called the triple point. And at the triple point, all three states of matter exist at the same time. So you have solid, liquid, and gas that can all be observed at this particular pressure and temperature. The other point is here on the top right. This is called the critical point. And beyond the critical point, we start to get in this zone of like a supercritical liquid. And the line between liquid and gas kind of starts to be blurred. Excuse me. So our critical point here is where the definition between liquid and gas kind of starts to become blurred in that zone. So a couple of notes about the phase diagram is that anywhere there's a border that contains both phases that it's bordering. So for example, point D, that's bordering the solid and the gas line. So as I'm on this line, both exist. If I cross the line, I'm experiencing a phase change. Crossing a border equals phase change. So if I cross at point E, let's say if I go from solid to liquid through the border, then the substance would be experiencing melting. And you could go back the other way, that would be experiencing freezing. So crossing a border means that you will experience a phase change. When you're reading these graphs, you will have temperature measured in degrees Celsius or Kelvin, which we already kind of touched on in our notes, and the pressure, I believe they're all in atmospheres for this type of diagram, but it could also be in kilopascals. Those are the two most common ones you'll see, but we did talk about torr, millimeters of mercury, psi, other units of pressure that are possible. But I think all of these graphs are in atmospheres. So when we are working through these questions here, these first four are just talking about, excuse me, they're just talking about the graphs themselves. So what is the main difference between a heating curve and a phase diagram? Look at those axes. So our heating curve is simply looking at adding heat over time and shows the melting and boiling point. But our phase diagram shows all phase transitions based on its temperature and pressure. I'm not going to write these. I'm just going to talk about them. You can write them down, though. You need to write them down. So as I'm talking, you write. Pause if you need to. What two variables alter the state of matter? Well, our phase diagram has pressure and temperature. Those are the two. In what state of matter would you expect a substance to be at high pressure most of the time? And low pressure, we discussed that, so I'm going to let you do that one, and then we can go over it in the Zoom if we are unsure. And number 4, describe what you would observe at the triple point. We also discussed that, so you should be able to do it. 5, 6, 7, and 8 are now using the phase diagrams to help us kind of get meaning out of it. So let's do one of these together, and then I will leave the others for you to try on your own. So what two states of matter are in equilibrium at point F? So here's point F. Remember, solid, liquid, and gas. You feel free to label them if that helps you. So on this line, that's bordering liquid and gas. So those are our two states that are existing on that borderline at point F. What state of matter does point G represent? We already wrote liquid. Our intermediate phase there. What phases are present at point B? There's our triple point, so all 3. Solid, liquid, and gas. And what two states of matter are in equilibrium at point E? So that would be this time bordering solid and liquid. Those are the ones present at that point. Moving into the other 3 graphs, you'll start to look at some potential changes in matter. Let's just do one of these together. So if you have a gas, so we got a gas at 200 Kelvin, so it's going to be kind of around here. Actually, it's probably more like here. And you raise the pressure to 3.1 atmospheres. Okay. So there's probably 3.1. Give or take. What phase change does it go through? So we cross the border from gas to solid. What phase change is that? That would be deposition. Okay, so use that same thought process to go through the rest of 6, 7, and 8. And then page 10, you're using the heating curve to fill in these blanks of what happens at each point along the graph.